Okay, I see some people still streaming in. We will give it about 30 more seconds and we will start. It's 6:30, guys. Welcome. For context, there are about 40 plus people who sign up for this revision event. Currently, if you can click into the number of participants, it's about 12 of you guys here. It's normal. I thank you for your time. I know the timing may be a little strange. If you are sitting in front of your computer now, you may even have your dinner beside you, and that's perfectly fine. I contemplated very hard about the timing for today. Um, I figured that before dinner, after dinner, it really didn't matter too much to me. Yeah, okay, as long as you are able to grab dinner, I'm fine. I didn't choose to start too early because some of you may be having CCA or extra lessons or whatever. Yeah, I don't want it to be too late also because I don't want you to like chiong your dinner then you come and attend this as well. Okay, so if you have your dinner plate beside you, that's perfectly fine. Or if I'm casted on your screen, I think that's even better. Okay, if your whole family is watching me also, that's perfectly fine. Okay, it has been a minute. It's 6:31. I shall begin now. I am already recording this session in case some of you, for some reason or another, you cannot attend the full thing. You are able to watch the recording at the end of the day. Okay, so on our side, we will be uploading all this onto YouTube eventually. Yeah, okay, but you being here really means a lot to me. Okay, I start with a bit of intro first. Okay, and of course, you must be interested in the lesson materials for today. Lesson materials, if you can see on the screen right now, there's a QR code. I will be pasting the Google link on the group chat on our Zoom chat as well. Okay, so you can click on the Google link to download this set of materials. What we are doing today will consist of general waves as well as light. Okay, I'm seeing a few familiar names. Hi, Krivish. Okay. Welcome. Anyway, the QR code I will be moving on already. So if you haven't scanned it, you can refer to the Zoom chat to download a copy of this. Okay, I've already done a sound check with some of you guys. Some of you responded to me. If I'm breaking up at any point of time, just type into the chat box to let me know. Okay, because don't wait until 1 hour later, then you're like, actually, we cannot really hear you. Okay, so don't wait for that to happen. Okay, for those who are not sure who I am, let me introduce myself a little first. We are going to spend a solid 1.5 hours to recap on these two topics that I feel a lot of students feel that you don't really understand. Okay, I'm here to assist you. I'm here to ensure that you are ready for your WA1, recapping waves as well as light. Okay, I cannot tell you that in 1.5 hours I will go in depth into these two chapters. That's a lie. Okay, you want to go in depth, I need at least 4 hours to deeply go into the content to start from the basics lah. Okay, but as Sec 4s, we have learned these chapters. I'm not gonna go like from the basics. Okay, I'm gonna be very exam focused into like what you need to know for exams. Okay, quick intro of myself. I won't spend too long here. My name is Gerald. People usually call me Mr. Gerald, Teacher Gerald, Gerald, whatever. Some students have resorted to calling me A. That's perfectly fine. Okay. Anyway, my name is Gerald and I teach both Chem and Physics. Today we are looking into Sec 4 Pure Physics. If you are here for IP Physics, no problem. You can absorb whatever that's going to be tested for O levels into your IP syllabus as well. Okay, so whatever the case, I'm here to teach you physics for the 1.5 hours today. I have taught for about 10 years now. And just last year, 2024 batch, I have 70 students taking O levels and a good 94% of them, quite happy to share this, attain at least a B3 at their O levels. Okay, and B3 to some of you may not be good enough, and I perfectly acknowledge that as well. Okay, some people, like what my students from last year experienced was like some people were jumping from like D7 to B3, and I think that's a pretty significant jump. Okay, so whatever target you are on is for yourself, and I wish to let you know that I am here to guide you towards that direction. Okay, a little bit about myself as well. Like I don't just teach and teach and teach. Like you, I have CCA and whatnot. I play floorball since secondary school. Ex-busker. Next slide, I will force you to listen to me a bit. Krivish probably heard before already, so I won't bore you too much. Okay, and I love Chinese TikTok songs, football fan, love Indian cuisine, and currently grooming a 1-year-old to be a human being. Yeah, currently she's like outside. I hope she doesn't cry halfway through our lesson or anything. But yeah, this is my 1 year old learning to be a human. Okay, at this point, I'm going to share sound. Okay, if you don't understand this song, it's fine. I'm just going to force you to listen to me. This is me bust. Okay, I shall stop here. If I'm like on your screen right now, I think it's even more cringe. Maybe your whole family listen to me. But whatever it is, I just wanted to let you know a bit of what I am. At no point in time should you be treating me as a school teacher slash professor where you just need to like sit down there and just like copy notes, copy notes, copy notes and everything. Then at the end of the day, then just like bow your head low and walk out. Okay. I will try my best to entertain your questions as best as I can. Okay, but I cannot guarantee that I can do it within this 1.5 hours. Okay, so if you have further questions like after 8 p.m., I'll be happy to stay back for a bit to like discuss those questions with you. Okay. Anyway, just some of my pictures last year with my students. Okay, anyway, something that may be more interesting to you would be like our branches, especially if you are like first time experience Overmug kind. I purposely wear the Overmug t-shirt also. Anyway, this is the cute logo of Overmug. Yeah. Okay. Anyway, if you are first time with us, we have currently 7 branches across Singapore. Personally, I teach at Woodlands as well as Coburn. Okay, but if you stay either maybe east side or west side, you may consider other outlets as well. Yep. Anyway, this is to share. 70% of our students achieve distinctions at their national exams, O levels, A levels. Okay, and our tutors are from NUS, NTU, those top universities. Personally, myself, I'm from NTU. Okay, pretty much coming towards the end before I start on general waves. Resources wise, this is what you see is going to be what you get. Okay, what I've uploaded onto the Google Drive, which you should have downloaded by now. If not, please check the Zoom chat. I have already posted the link there. Okay, we have notes, we have revision worksheets as well. Okay, and personally, my belief is after you understand the content, you must put into practice. Okay, which is why today we are going to focus both on content as well as questions. All right, that's about it. Personally, this is my strongest belief after class consultations. Yeah. Okay, so if you know any of my students or if any of my students are here, you would know that I would reply to your message as soon as possible. Okay, maybe sometimes I need a few more hours. Maybe my baby is crying or something like that. Okay, but I'll always get back to you on your questions. And even if you send me at 12 a.m., sometimes I reply. Yeah, but most of the time, maybe I sleep already, then next day I'll reply you. Okay, that's about it. Okay, this is the meme that I usually show my student. I shall not go too much into it. It's basically exam versus you and me. Okay, we are here to tackle the exam together. And lastly, a bit cringe, but I really want you to believe, since you have spent time to be here, that you are truly the main character. I'm going to push you towards the correct direction to do well for your WA1. Okay, at the end of it, I will ask you to scan this QR code to see whether you want to leave a Google review. Okay, but let's leave that to the very end. Let's jump straight into the content now. This is the first page that you should see after you download the correct lesson material. Okay, what you should see on the first page will be this secondary 4 physics, general wave properties and okay, and that's our focus for today, GWP learns. Okay, for those who just came in, if you have your dinner plate beside you, that's perfectly fine. Okay, I don't need, I can hear you munch also if you really want to. Okay, but that's perfectly okay. All right, we're going to jump straight into the content portion first. Give you a bit of a heads up. The content portion, we won't dwell so much into it. I'm going to highlight very specific points that are important. Then we will dive into the questions to show you like how do I apply this content into exam. Okay, and there are certain things that I would say in this chapter, schools don't really emphasize too much. Okay, not because it's not important, but because they want to go into the basics. They want to build you towards some, I don't know, they call it now active learning or something like that. Okay, but we are going to be very exam focused here. Let's look into the first general wave properties. We go into the first page of the contents. Just make sure I'm sharing the correct screen first. Okay, everything is good. I once spent 2 hours recording my lesson and I muted my mic. Yeah. Okay, my students would know this. I'm very paranoid about recording. Okay, let's go into the idea of waves. The idea of waves is the following. There are 2 points that you definitely need to know, and I'm going to zero into them straight. Okay, number 1, This is a source of disturbance, wave source. Wave source is nothing more than a source of disturbance. If we don't disturb the particles will remain at equilibrium. If they are at equilibrium, there will be no wave. That's it. So I disturb the particles. They either move perpendicular or parallel to the direction of the wave. Right? Okay, I'm going to copy the link again for those who just came in. No problem, PQ. The link to the PDF is copied already, okay, on the Zoom chat. Right. The second thing you need to know will be transferring energy without transferring the metal or medium itself. I would say these two key properties, sometimes they can test. Okay, I would say the source of disturbance is the important thing you need to realize. Okay, but without transferring the metal is a second crucial point as well. Okay, but my goal here is for you to truly understand what you are seeing. You are seeing longitudinal, you are seeing transverse. We are going to zoom into these two individually pretty soon. Okay, so let me move on a little first. These two waves that you see over here, the only thing I need you to realize for now will be that this is the equilibrium positions, EP for equilibrium position. All this center of compression and rarefaction, all these are also equilibrium positions. Okay, and we will get to that very soon. In the questions later, we will actually go beyond the question as well for you to think further about how to plot a graph in waves. Okay, so the equilibrium position is basically the position where, if there's no source of disturbance, where the particles are going to be. Right? The wave motion movement of energy wise, I will look past this, but the idea is the following. Exam hack over here, wave motion, whenever you see, for example, a rope from A to B, what you need to do in exam is the following. You see this entire wave may not be so easy to visualize things. What you can do in exam will be draw this dotted line in the middle. This dotted line in the middle will be very helpful for the following reason. This shows you equilibrium position. Pretty much waves, how I love to imagine this, and I want you to also imagine this, is like just a pattern. I have a pattern that repeats itself again and again and again and again and again. This is literally what waves is about. Okay, we're going to zoom into certain key terms that I will not emphasize too much on, but I want to zoom into one specific thing, which is your speed of wave. Okay, speed of wave, again, I want to emphasize on what schools don't usually cover. Okay, this two, t equals to 1 over f, f equals to 1 over t, is definitely something you need to know. To summarize the entire thing, for those who are a bit confused on all these terms, period, we are always referring to time. Frequency, we are always referring to number of complete waves. At no point in time for pure physics should you be memorizing plainly, just like, oh, period is like time taken for da 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 da. Okay, if you want to memorize the definition, not harmful, okay, but if you don't understand, you still cannot solve questions. Yet, so I always emphasize to my students that you need to know what you are really learning. Last thing before we move on, speed of wave. Speed of wave is not the same as speed of particles. Later in one of the questions, we will discuss this idea again. Okay, speed of particles is each individual particle, how they are moving either left, right, or up, down. Speed of wave is the speed in which the energy is being transferred. Okay, so there's a difference between these two. Later, we will make use of a shuttle run example, right, to try to imagine this a little better. Okay, lastly, wavefront, to quickly sum up this, right, wavefront is basically that imaginary line. Okay, so wave is not always just like one of this. Wave will be multiple waveforms. So wavefront is simply joining up, for example, or the crest. Joining up or the crest. Therefore, distance between two wavefront equals to wavelength. Okay, that's simply the idea already. Some key terms out of the way. I want to straight away jump into transverse. Okay, for transverse waves, I need you to think of the following. Okay, you see in the notes, the box at the top, right? The kinetic wave display. If you don't know where that thing is, right, is this thing. Okay, at Changi Airport, you will see this. There's some crazy news that happened a few years ago. I think someone tried to climb this entire thing. Okay, but from this, what I need to see is the raindrops, right? The kinetic raindrops are just moving up and down. But feels like the energy is being passed along. And that's exactly the idea of waves. Okay, if you are a big hater of the chapter, hear me out. For transverse, if I show you the diagram below, focus on one particle, any particle you want. Okay, just look at one particle and convince yourself how is it moving. Pausing here for dramatic effect. No lah. Okay, pausing here for you to intentionally focus on one particle to see that it's actually just moving up and down. Right? But energy seems to be passing from left to right. And that's exactly the idea of transverse wave. Okay, so the particles are moving just perpendicular, but the energy is being passed forward. At no point in time, if you're thinking or your school teaches you this, the particles are on a roller coaster, like going along the entire wave. This is completely wrong. Okay, so throw the idea out of the window already. Stop thinking about that. Particles are not sliding along the entire wave. It's false. All right. That's about the idea of transverse. I'm going to move on. I want to go into the question soon already. Okay, so for transverse, that's basically the idea. I won't jump too much into it anymore. Yeah. Sorry, Zoom suddenly tell me my camera is on, so I was a bit confused. Okay, same thing. If you lose touch of me, please let me know ASAP. Okay, I'm jumping on straight to the next part, to the next page. This page on commonly tested question 1, I just want to bring to your idea of like how to imagine how a wave is moving. Okay, whenever these kind of questions appear, some schools have taught this, some schools maybe haven't learned. Whatever the case, I have something to tell you that is going to be new one. Okay, some schools have already learned the exact method to approach this. But what I want you to truly understand going out of the Zoom today, right, will be this wave. I go with the exact method first. Exact method is look at the direction of travel. Control C, Control V. Copy, paste. Copy, paste the entire wave to the right. In this case, you can see that P is going to move down. Okay. Something that schools don't usually run through is the following idea. Why on earth do we Control C, Control V? Why do we copy paste? This brown color line that I've just drawn over here is the exact wave form that you will see when the particles move. Does particle P move to the left or right? It doesn't. Particle P, the only possibility is either move down or move up. By drawing the next wave here, right, what you can see is the following. Particle P will move down. Okay, and this is what usually schools will cover. That's all, they finish here. What I want you to see more is the following. This entire wave is made up of a lot of different particles. So what we are actually doing here is we are trying to see how all these yellow particles are going to move next. By drawing in the brown line, you are actually telling yourself how will the yellow particles be or where will they be at the next instance. Okay, so that's why we will see P moving down. That's it. Okay, and to complete this question before we go on to longitudinal waves, particle P, we want one complete cycle. Okay, in waves, when you think about the particles moving, always think about 4 different parts. Okay, split up into 4 quarters to think about this. Particle P is currently at equilibrium. So how will one whole complete cycle be? Since we decided that it will move down, next can only be up. Okay, just like life like that. You are at your lowest in life, you have to go up. Okay, so we'll be down, up, down. These 4 different parts should be what you are describing when you describe the motion of the particle. Okay, I'll be going past this already. I'm moving on next to transverse wave. To longitudinal wave. Right? If you can help me skip a few pages down first, if you can go through some questions at the same time, I think it will be helpful for you to be able to link up certain ideas. Okay. If you can flip a few pages down, you will see question number 2, which is a transverse wave question. Okay. I don't have enough time to allocate for you to like try it out. So at the same time, if you are already reading the question, please feel free. Okay, but we are going to dive into how to solve the question immediately. Okay, the diagram over here shows this wave with particle P at the crest. When you're at your highest point in life, you are going to come down. Okay, when you're at your top, you're going to come, the only way is down. Okay, so what this question is really telling you is the following. Question wants you to find out particle P after half a period. Note that period is time taken. Time taken for what? Period is actually time taken for one complete oscillation. Meaning, if I think about how particle P will move for the entire period, right, will be the following. P will move down, down, then back up, then back up. Okay, so what's half a period? You're just going to erase this line, erase this arrow. Therefore, P is going to move all the way down to this position. That's it. Question tells you amplitude is 2 cm. Wavelength is actually a distractor. Okay, so amplitude, if it's 2 cm, this is going to be 2 cm as well. Therefore, this displacement over here must be negative 2 cm. That's it. Answer B. Okay, so we are going to go with like how to solve questions like that. I'm moving on to question 3 for a bit first before we go into longitudinal. Okay, question 3 shows again a transverse wave. Okay, this is slightly different. This is wave traveling to the left. If it travels to the left, your job will be to copy paste to the left. And that's it. That's the idea already. Okay, and I've explained to you exactly why we Ctrl-C, Ctrl-V to the left or to the right. Because we want to see how the particles, or rather all the particles on the wave, where they are going to be in the next instant. Okay, so if I go with the copy pasting idea, I'm done. My brown line again is in already. I can see how P and Q are going to behave. Q is coming down, P is going up. That's it. Okay, so Q downwards, P upwards. The only possible answer is option C. Yeah. Okay, I'm going to jump back to longitudinal waves to discuss. Okay, if you can go back a few pages with me, we are going back to the idea of longitudinal. Longitudinal is not difficult to understand. Intentionally, I selected some questions that are longitudinal waves. I feel transverse, you may have a better idea. Okay, but just now, if you saw question 1 when you're scrolling down this entire document, right? We are looking at how the particles are moving away from their positions parallel. Okay, and it's purposely on. Longitudinal definition, I won't go through too much already. Okay, but just know that it's parallel. Compression, rarefaction are regions. For those who are still thinking that compression, rarefaction is a specific particle, not correct. Okay, compression, rarefaction are regions. The whole set of particles determines whether it is a compression or rarefaction. Okay, so what are we focusing on, right? Is always into the smack in the middle of a compression and rarefaction. Okay, because we are interested in, for example, the wavelength, we want to see how from one compression, or rather center of a compression, to the center of another compression, this is going to be the wavelength. Okay, that's why this wavelength over here shows you the following. This C over here that I'm writing is not to say that this is the entire compression. This is the direct center of the compression. Therefore, the distance between these two shall be your wavelength. That's the idea. Okay, so I'm sure you have learned sound waves as well already. So I'm just gonna put it out there for your understanding. Okay, how does sound wave travel? If I don't talk, just like that. Basically, you cannot hear anything, correct? Okay, so what am I doing when I'm talking, right? I'm literally like disturbing the air molecules around me. Okay, that's why the sound wave is able to travel. Okay, physically, if I see you, it makes a bit more sense. Now we still need to think about the microphone on my laptop, then the speaker on your laptop, whatever. Okay, but that's the idea. I'm disturbing the air molecules. Okay, what I need you to see is like how to visualize this, right? A slinky coil or silky coil will be the easiest way to visualize this. Okay, but as well, you also can be thinking about something like this. So the compression and rarefaction of air molecules is something like this. This tuning fork, I think, is the most common example that you can properly visualize. So same thing, I'm just disturbing the air molecules again, then they vibrate this way. Again, forming a series of compression and rarefaction. What you see on this screen now is currently, I can see quite clearly, energy moving from left to right. Again, are the particles really moving all the way to the right side? The answer is no, it doesn't. Right? Because the particles are literally just moving this way. But the energy can be passed forward in the wave direction. Okay, enough of the visualization. Let's go into the exam skills already. Okay, exam skill wise, let me go through this particular page first before we straight away jump into one of the questions already. Okay, on this page, I just want you to be able to differentiate properly displacement time versus displacement distance. These two graphs are completely different. Okay, and I'm sure schools will emphasize the following, so I'm not so concerned. Displacement time, the x-axis is time. Therefore, you calculate period. Okay, and I'm sure majority of our schools emphasize this already. Okay, my focus for my lessons is always I want to identify things that schools don't say. Okay, because you are here to upgrade yourself. Okay, and after this, you are supposed to walk away thinking, oh, shucks, why my teacher never tell me this? Okay, and if you are able to do this, I basically achieved what I wanted to. Okay, displacement, distance, no problem. I think schools will emphasize this as well. Distance on the x-axis, therefore wavelength is what you can see. Okay, normal, right? This is what you learn in school, right? But what I want to emphasize further is this. Okay, what schools don't really emphasize on and what I want you to know is this. Displacement time, we are studying not the entire wave. Okay, when you see a wave, it's normal. You just see, like that, like waveform. Okay, but what truly separates you from your peers who are not in this session, for example, okay, is the following. This graph is actually studying one particle. I'm literally studying the motion of only one particle as to how it moves. Okay, is the particle moving along the entire wave? Is it sitting roller coaster? Again, the answer is no, it isn't. Okay, I'm seeing some new people coming in, so I'm going to copy paste the link again, just in case you need to download the set of materials. Okay, I pasted into our Zoom chat again. Sorry for the distraction. Okay, I'll come back. So displacement time is actually of one particle, but displacement distance graph is of particles. What do I mean here is when I look at the displacement distance graph, I'm literally looking at different particles at different points of the wave, studying where exactly they are. But displacement time, I'm only looking at one. Basically, I study this one particle. This came out as an O-level question before. That question requires really deep thinking. I'm not running through that question today, okay, but this idea will lead you to solve that question when you look at it eventually. Okay, when I look at only one particle, if I say the displacement goes up, what do I mean? The particle is literally moving up. Okay, next, the particle displacement comes down. What am I saying? The particle moves down. That's it. This is your equilibrium position. Next, the particle moves down again. Literally, it goes down, then it comes up. This entire purple thing that I traced is literally this down, up arrows. So that's good? Okay. At this point in time, some of your questions in your head, if I can echo your thoughts in your head right now, I believe some of you may be thinking, sure, so is it possible for this to be a longitudinal wave? Okay, ding, jackpot if I hit some of your thoughts. Okay, but I believe some of you will be thinking through something like this right now. Okay, the answer is yes, it can be. Okay, and I'm going to show you exactly what I mean before we move to question 1 already. If I draw an equilibrium position of a particle, this is a longitudinal wave. What I'm trying to show you here, I'm going to erase the purple stuff for now. I'm going to go with green for this. Okay, first thing, the particle started at equilibrium position, then displacement increase. We know for a fact that longitudinal, they must move this way. All right. This particle is therefore going to move in either of the direction. I'm going to purposely define just for the sake of this example, right to be positive. Okay, so whenever it goes above the x-axis, I'm going to say it moves to the right. Okay, some questions will differ. I'm just giving an example. Okay, what am I trying to show you here is the following. This particle moved this way. Then it moved back down, meaning going back to equilibrium position. Okay, so positive is right. So when it goes back to 0, it moves to the left. What about here? Continue moving to the left, then it moves to the right. That's it. Okay, so what I need you to see is displacement time is actually studying one particle. This one particle is going to enable you to see its complete oscillation. Okay, that's why you also can see the period from here. So this particle took 4 seconds to move right, left, left, right. Right? And that's the idea already. I want to move straight into question 1 right now. Okay, sorry, I'm toggling a little. Okay, help me zoom into question 1 of the MCQ. Question 1 of the MCQ is a question where I want you to think beyond this question. Okay, we are going into light pretty soon. Okay, so if you are only tested on light, bear with me here, okay, because there are a lot of things to cover for wave as well. Okay, so for question 1 over here, I have particles in equilibrium position in figure A. Figure B, that's where the particles get disturbed. Okay, this question is basically just asking you to find a statement best describing the particles in figure B. Sure. Okay, MCQ, are you likely to see this question again? Maybe not. But if you truly understand lend me your ears for the next 2 minutes, okay, I want you to upgrade yourself in terms of how to think about how the particles are moving. Okay, how are the particles moving over here? I'm going to zoom in a little. Okay, on your screen, I hope on your notes you are taking down as many things as you can. Okay, because this will determine your understanding rate. What I want you to see is particle A still remain at equilibrium positions. Okay, when you look at a complicated diagram like this, first thing is go and identify for yourself in figure B, where is the center of the compression and rarefaction first. Compression is squeeze together. Rarefaction is go apart. Okay, so the center of compression and rarefaction, keep in mind, is always at equilibrium positions. Therefore, particle A is actually what I want to consider. Particle E is also what I want to consider. Particle I is also what I want to consider. Particle N is also what I want to consider. Okay, so all these are either center of compression or rarefaction. That's it really. So if you see compression coming together, this means that this is center of compression, center of rarefaction, center of compression, center of rarefaction. Okay, and this idea is pretty familiar, I believe, for most of you. Okay, but even if it's not, this is where you can pick this up from now on. Okay, so what I want you to see now is the following. Question intentionally labeled all these alphabets to help us, not for fun. Okay, the B was at this position. What happened? B moved here. Can you see? B was at this position, right? So B moved to the left. C from this position moved to the left as well. D from this position moved to the left as well. Can you see where I'm going with this already? If I trace for every single thing, which I'm not going to do, so F, you can see that F is moving from here to here. G is moving from this position to this position. Okay, then H will be moving from this position to this position. Something like that. Okay. So what I wanted you to see here is actually you can see how the particles are behaving. It's not randomly that the particles are moving this way. It depends on the source of disturbance. Okay, I'll go with the options. I just want to go through one particular option that I feel usually people will get wrong, which is option A. Particles B and H are one wavelength apart. Okay, B and H are difficult to imagine simply because they are not the equilibrium position. Okay, so what you should be doing for this kind of questions is, look at particle B, look at particle H. See whether they are in phase or not. Particle H, what has happened? Move to the right. Particle B, move to the left. Okay, That's why it is never possible for this to be true, because B and H are not in phase. Okay? In phase meaning they move in the exact same direction all the time. Okay. Okay, particle C moving at maximum speed. This is something that I want to run through with you using the idea of particles. Okay, so particle C moving at maximum speed is actually incorrect. Okay, air momentarily at rest. Yeah. Okay, so particle C moving at maximum speed is actually false. Where or at which positions will the particles be moving at maximum speed? The answer is actually only particles at equilibrium positions move at maximum speed. Okay? And if I just give you a very easy example, like shuttle run. Shuttle run, you need to run to grab the blocks, then you come back. Then you go again, then you come back. You are literally like a particle. You are moving there, coming back, moving there, coming back, like a cycle like that. Okay? At which point will you be moving your fastest? Actually, somewhere in the middle. In the middle, you will be like running your fastest, after which you will start to slow down because you need to grab the block. Okay? So particles at equilibrium will always be at the maximum speed before they start to slow down a bit because they know they need to change direction. Okay, so particle C is not at equilibrium, therefore not correct. Okay, I'll go with the correct answer already. Particle G at maximum displacement is actually correct because particle G is at this position over here. It moved 1, 2, 3, 4, 4 small squares. This 4 small squares is actually maximum displacement, which means that this is actually your amplitude. That's it. Okay. Okay, so this is the idea of how to properly understand how the particles are behaving. Okay, and one final thing for this question is if I can upgrade you in terms of your graph drawing as well. I'm going to draw in pink color. It's going to look a bit ugly because it will overlap with the words, okay? But it's okay. I want you to just be able to see the following. I purposely draw below so that you are able to see more clearly. I'm drawing actually a displacement distance graph. From this diagram over here, actually you are able to draw yourself, or rather you are expected to be able to draw this displacement distance graph into your diagram. Okay. And what do I mean by this? Displacement distance, particle A remain at equilibrium. So my point is basically here. Particle B has moved to the left. I am going to take left as positive. I purposely define this way. Left as positive, I'm going to see particle B moving to the left. Particle C is moving 1, 2, 3, 4, 4 small squares to the left. This is maximum displacement, which means that our peak at particle C. Particle D to the left as well, but only a bit. Therefore, it comes down. Particle E is at equilibrium position again. Can see what we are doing? I'm trying to show you how the particle's movement can actually be translated onto a graph form. Okay. Then when we go below, right, I'm going to change color for you to be able to see this a bit more clearly. I'm going to intentionally go with green. Okay, what you can see is G is actually the maximum. So when I draw a graph down here, it's actually, I reach F, then I continue to reach G at the maximum displacement, or rather for this case, minimum displacement, before I come back up again to complete the wave where I is at equilibrium position. This cycle repeats. Okay, so this is exactly how you need to visualize waves to properly understand in terms of each particle, how is it behaving. Okay, I shall move on from this question already to the last part of waves. Last part of wave will be water waves. Okay, and water wave I like to teach via this. I won't go with the explanation of tsunami because job students will usually like disagree with me. Okay, but that's fine. For this, what I want you to know is S, S, S. When I go shallow region, I will slow down and my wavelength will become shorter. That's about it. Okay? And one way to imagine this one I would share with my students as well always will be like if you put Joseph Schooling into a very shallow pool, will Joseph Schooling be able to do all the butterfly strokes, all the freestyle, the breaststroke and everything? Can it? Right? Because it's too shallow. Literally, he is as shallow as like I go in, then like his chest touch the floor, that kind. Nah, okay, then he won't be able to carry out all the nice strokes already. Okay, compared to if you put him in a deep pool, he can do all his like beautiful strokes and everything, so he will move faster. Okay, this is similar to waves as well. Wave, when I go deep, I'm going to go faster. Shallow, I'm going to go slower. As a result, shorter wavelength. That's the idea already. All these words over here that you see below, right? I'm going to summarize it very easily for you. V equals to F lambda. V equals to F lambda. Frequency doesn't change. Frequency only depends on the source of disturbance. If source of disturbance doesn't change, frequency doesn't change. Alright? V and lambda, if I slow down, because I go shallow, my wavelength will therefore decrease. This is the exact reason why we are able to get shorter wavelength as well. Take a moment to digest this a little. I'm going to move on in 10 seconds to MCQ number 4. Right. Again, at any point, if you have questions, you can leave it inside the chat box. I may not be able to straight away attend to them, but I'll try my best. Okay, question 4 is a simplified question basically. Okay, the commonly tested question in the set of notes that you see above will bring this idea up a bit better. Okay, but I shall move on with this and the structured question already. Then I want to sum up waves. Okay, so this is as simple as this. Water wave move from deep to shallow. If you have understood what we have discussed, you would immediately be able to come up with this, even if the question doesn't tell you. I would say question don't need to tell you this because you should already know this, right? So if you go with the SSS, that's it really. SSS tells you that when speed decreases, your frequency remains changed. Frequency decrease is therefore wrong. Frequency decrease, therefore wrong. Answer is either B or D. That's it. With V equals to F lambda, when speed decrease, frequency same, wavelength must come down. Option D is the only correct answer. Okay. Of course, there are questions that are going to have like numbers for you to play around with. You can look into your the notes that's provided for you. There are some common questions there for you to think about. Alright, that's it. I'm moving to the last structured question before we sum this up. For those who have missed out on the answer for the MCQs, the answers are C, B, C, D. Okay, questions 1 to 4, C, B, C, D. Okay, again, not pausing here for dramatic effect, but for you to take this down. Okay, I'll go to question 5, the structured question. Then we will start lines. Question 5 has this idea of, again, I purposely choose one. Okay, I was thinking very hard, like whether I should give you the normal transverse wave. I feel you struggle a lot more. You probably struggle a lot more in questions like this. Okay, so same thing. These straight lines over here are usually given as the equilibrium positions. These straight lines are when the particle experiences no source of disturbance. Right, now that the particle experiences source of disturbance, we see the particles move. Particles move such that they are at different positions now. So basically, like from this equilibrium position, this particle moved here. This particle moved here. This particle moved here. This particle moved here, here, equilibrium. Okay, same thing as what we were doing just now as well. I told you, when you see this, go and find out the center of compression and rarefaction first. Can see how already? They already labeled for you the centers. Q is like coming in together. Therefore, Q is actually center of compression. P is particle going further away. Therefore, P is actually center of rarefaction. R particles are also going away. Therefore, R is also center of rarefaction. Okay. So this is exactly how the particles are being displaced from their equilibrium positions. Why are the four squares max displacement? Ooh, is this for the previous question? Okay, can. Jovin, I will get back to you later. Yeah. Okay, I shall move on with this first. So this 5A over here, right? I have the particles moving into each respective positions. And for the other particles, you can see I purposely put in green, then moving to the left. Okay. For 5A, I just need to show why or how does this diagram show that it is a longitudinal wave. For questions like this, go and define. Why? Because you need to convince the examiner that you know what is longitudinal. Okay. So go with the exam trick here more than like, oh, I need to faster write down everything. Okay, the answers is flashed to you. Okay, you can take them down if you want to. But what I am trying to tell you is questions like that may appear again. And what you need to tell the examiner is, I understand the definition of longitudinal wave. This diagram shows to me that the particles are moving parallel to the direction of the wave. That's it. Okay, we're gonna do part 5B together. Part B, we have to figure out the amplitude of the wave by drawing an arrow. Okay, I've drawn multiple arrows already. Amplitude means what? Amplitude will be maximum or minimum displacement. Sorry, maximum or minimum displacement. Okay, but question over here. Maximum displacement. Going from left to right. Okay, so if I want the amplitude, it is always the case where I can decide whether I want to go left or go right. Both will be fine. Okay, so answer to this will therefore be all this. I shall erase the arrows that are not correct. So the maximum line, the longest line, will be the answer. So either you draw the blue one or the green one, you'll be marked correct. Crystal's question is, why can't I put that there's points of rarefaction, you mean? Rarefaction and compression, since it is shown in the figure. Accept. Crystal's alternate answer to part A is, there is a series of compression and rarefaction that I can see in the wave, which indicates to me that it is a longitudinal wave. Accept. Yeah, thanks for pointing it out. Okay, so part B's answer is given already. So either the blue or the green arrow. No problem. Okay, part C is the more challenging one. Time taken for the wave to at position Q to move to position R. Okay, and if you don't understand truly the longitudinal wave, you may suffer a little. Let me help you out here. Position Q to position R is how long? It's not one wavelength. Okay, so that will be the most common mistake. This is actually just half a wavelength, meaning the time taken for the wave to travel half a period. Okay, so the time taken that I want over here is actually half a period instead of one full period. Okay, so to go from Q to R, basically I need half a period. That's it already. So for a question like this, I'll give you the answer first. I want to derive this together with you guys. Okay, so the time taken here, how can we do this? What we can see over here is 1 cm given to us. This 1 cm is not one wavelength, right? This 1 cm is actually between this and this. What I can find from this is one full wavelength. One full wavelength will be 1, 2, 3, 4, 5, 6. Half a wavelength, 7, 8, 9, 10, 11, 12. This entire distance over here is one full wavelength. Therefore, what you can show here is wavelength is 12 cm. Okay, which is 0.12 meters. Always convert to SI units to play safe. Okay, and now what I want to find will be the time taken for half a period. What I can do, V equals to F lambda. Okay, if you are familiar with this, you would be able to tell me this straight as well. Lambda over period is also the speed. Okay, what do I have? I have the speed 1500. I have the wavelength 0.12. I can now find period. Okay, I'm not going to solve the math for you or anything, but if you can come out with this, you're done already. Okay, so at the end of it, I can calculate the period, and my final answer is half a period. Half a period in your calculation should be 4 times 10 to the power of -5 seconds. That's it. Okay, and to wrap it up, 5D, softer, lower pitch passes through the medium now. Okay, this is a bit more related to sound. Okay, I purposely leave some blanks for you to think a little. Okay, just a quick 10 seconds maybe for you to think about this a little. Okay, because we should be familiar that loudness depends on amplitude. Pitch depends on frequency. Right? So the particle will actually vibrate with a answer, smaller amplitude. The second blank is more challenging. Lower pitch, I think you all can tell me that it is lower frequency. What does lower frequency really mean to you? Lower frequency means less complete wave in 1 second. What does that determine about the movement of the particle? I cannot say less complete wave because I'm talking about the particle movement. Instead, I should be talking about particle moves more slowly. Okay, because I only complete one wave, or rather I complete less waves per second, therefore the particle must move more slowly. Okay, in this case, sound, so the particle will move left and right more slowly. And that's it. Right? And that's waves summed up. I'm going to move on next. To quickly answer Jovin's question first, right? Jovin's question just now was why for question 1, 4 squares is the maximum displacement. Okay, so for Jovin who asked this, hear me out for just 10 seconds. What the 4 squares mean is I have compared all the different lengths. 4 squares when G, right? Yeah, particle G is moving from this position. It moved 1, 2, 3, 4. This is the largest distance that any particle has moved. Okay, so what you need to do is to try for all the particles and realize that this is the maximum. That's it. Okay. Moving on to light. No problem. Okay, and moving on to light. Chapter that usually flows. I would say some Sec 4s, maybe you already learned this last year. Okay, so if you have, or in case your WA doesn't involve this really, stay with me. I think you will be able to discover more things than you have learned either last year or this year. Okay, especially total internal reflection. Okay, I would say this chapter is basically broken down into 4 different parts. Okay, basically reflection, refraction, total internal reflection, as well as lenses. Okay, my focus of today is more towards total internal reflection and lens. Okay, to debunk some of the myths that these 2 concepts very difficult, something like that. Okay, but allow me to spend a little bit of time on reflection. I'm not gonna go through reflection is this, reflection is that. Okay, again, I'm gonna zoom into exam stuff. The idea of reflection is not difficult to understand. I'm going to actually skip past the first page. Okay, I want you to think about the second page first, before we go into the third page example. Okay, ray diagram is honestly haven't been tested as a drawing question for quite a while, for O-levels. Okay, but what I need you to know is how to solve certain questions, even if you don't need to use very nice lines to draw and everything. Okay, the steps to ray diagram is always image to eyes, object to mirror. That's it. Okay, image to eyes, object to mirror. Why I want you to know this is because of the common example on the next page. Okay, or rather next page, sorry. Okay, next page characteristics. I just need you to know what virtual is about. Virtual means cannot capture on screen. I would say it's one of the commonly tested definitions. Okay, so make sure you are aware of this before you move on. Okay, next, I want to go into this question directly for us to discuss one point. This type of questions here, there are 3 steps that I need you to internalize. The first step is literally what we have discussed already, how to draw ray diagram. The answer key is given below to you, sure. Okay, but the 3 steps over here that I need you to do is, number 1, draw in image. Next, image to eyes. Third, see whether ray gets cut off. Okay, so if you always go with these 3 steps, this type of questions can solve pretty easily. Okay, and what do I mean by getting cut off? Cut off can either be never hit the mirror or getting blocked by the obstacle. For this question here, what I needed you to see is after I draw in the image, I draw in the line into the eyes, feels like all the objects can see. But when I draw the line from the object to go onto the mirror, these 2 object light rays get blocked by the obstacle. As a result, the person cannot see object A and object C. Okay, that's the idea of determining whether you can see or cannot see a particular object. Okay, I would say reflection is a bit underrated. Okay, because some people just think, as long as I know angle of reflection equals to angle of incidence, can already. Okay, but difficult questions are not just there. Okay, so this is one common difficult question. Next common difficult question might be similar triangles. Okay, and similar triangle is this idea over here with this question. I'm just going to go through this question. I'm moving on to refraction already. Okay, this question over here has similar triangle involved because trigonometry is quite commonly tested in reflection. Okay, either you use Tuakaso, which is your tangent, cosine, sine, which I won't elaborate too much, okay, or some questions will give you similar triangles. Similar triangles are in this form. This triangle over here in brown and this triangle over here in orange are similar because their angles are all the same. Okay, I don't need you to prove in physics why they are the same, but you need to be able to tell that they are the same. Next thing is, how do I identify the corresponding sides? 30 cm and 20 cm are corresponding sides. Meaning, 30 divided by 20, the ratio is going to be the same as another corresponding sides. So where we are going with this is actually this and this in green are corresponding sides as well. Okay, so if I call this x, this must be 80 cm minus x cm. Therefore, answer is actually 30 over 20 equals to 80 minus x over x. Because similar triangle, S, S, S. All the sides must be in the same ratio. Okay, when you solve for x eventually, you will get x is actually equals to 32 cm. However, help me correct this answer key a little here. Okay, because question is asking for point of incidence to the screen, which is actually this 80 minus x. Therefore, final answer should be 48 cm. Okay, answer on this note should be option C. Okay, and that's basically it that I will go through for reflection. I want to jump straight into refraction. 2 pages from here. Okay, the idea of refraction is the following. Okay, what I need you to see in refraction is like going into a theme park. If the theme park is super crowded, you cannot move very fast. But if the theme park is like no people, or I don't say theme park, maybe just a flat piece of land, like maybe some grass, okay, where you can run very, 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 very fast. Not crowded one, means I can move really fast. Crowded place like a theme park, I move very slow. The idea of refraction is actually this. Okay, why do light rays bend? Because they change speed. When they change speed, they bend. How do they bend? You will see the pro tip below as well. Okay, and this is what I love all my students to be able to do. Okay, so FAST is actually about when I move faster, I bend away from normal. Slower, I bend towards the normal. Okay, and if you use this quick hack, it's going to be very easy. Why? Because if you take a look at the following here, this light ray, quite obvious, bends towards the normal. There are some questions that might not be so obvious. Therefore, exam tip over here will be always extend this light ray as a check. Okay, extend this light ray to check is it really bending towards or away from the normal? Extend it as if it didn't bend, then tell yourself, oh, this is bending towards the normal because it's going nearer to the normal. Same idea for the other side. I extend, I see it bending further away from the normal. Therefore, confirm away. Your conclusion should be this, that this is actually going slower. Therefore, towards. I am applying ST. Okay, the other diagram over here will be going faster. That's why I bend away from the normal. Keep applying FA. So this is how refraction occurs. And I think the trouble with most of you who are tuning in for light, right, will be, I don't know, right, like the calculation portion. Okay, if you are that kind of person, hear me out on the next page. This N over here, you will see different ways to find it. Okay, to give you a bit of a very fast overview on this, N must be more than 1. No matter what, it must be more than 1. Okay, there's a way that I usually like my own students to do this. Okay, I'm not going to force it upon you in this lesson. Okay, but this N equals to sine I over sine R, usually I don't use in class. Okay, but for the purpose of this, I'm going to stick with this for now. Okay, so only my students will know why we usually say in class. Okay, and that's fine. Okay, the idea of sine I over sine R is, I just want you to know that you always put the bigger angle at the top. Bigger angle at the top. Okay, so that this will always be true. You need to always point yourself back to N is more than 1. Okay, and this will be formula number 1. N equals to sine I over sine R. Okay, formula number 2, refractive index. N equals to C over V. Take note here, because we are in the topic of light, right? Sometimes this vacuum, speed of light in vacuum can also be speed of light in air. Okay, we are basically assuming for them to be about the same. 3 times 10 to the power of 8. Exactly the same thing I want you to see here. This numerator over here, once again, is bigger. So that N is still more than 1. Okay, formula number 3 will be real depth over apparent depth. I won't go too much into this. Okay, the ray diagram for refraction, I won't go too much into it as well. Okay, but this critical angle idea, I'm coming to it next. Okay, which I believe will be the difficulty for most of you. This total internal reflection idea appears difficult at first, okay, but hear me out. In the next 5 minutes, I want you to debunk this once and for all. Okay, total internal reflection, do not read these 3 paragraphs first. Okay, if you force yourself to read all these words, it won't make sense. Help me out here. Follow me with the diagram below. Okay, the diagram below shows you the following. The diagram shows you normal refraction happening. What I want you to see is, I am trying to play punk. Okay, I'm trying to poke this fella, this friend that I have, I don't know, always like maybe got anger management, I don't know. Okay, I'm trying to poke this person until a point in which this person explodes. Something like that. Okay, so what I'm trying to do here is, normal refraction is happening. Okay, then I purposely go and increase the angle of incidence. Okay, I'm drawing this arrow in brown. What will happen as a result is, my angle of refraction is going to increase as well. Next, I bend even further. I continue to bend. I keep bending, this will keep increasing as well. What is critical angle? Critical angle is I continue to increase until this line can no longer bend out. Instead, this happens. I'm going to continue to use this diagram to show you there's a particular angle that this can no longer bend out, but it bends along the surface. That's the idea really. And this is exactly what you see here. Therefore, this angle of incidence is known as your critical angle. This critical angle is the angle of incidence, so the angle of refraction is 90 degrees. Done. So what is TIR, total internal reflection, is where I push this person beyond his or her limits. I already know she damn angry already, but then I go and continue to disturb her until she bursts. I already know I cannot bend anymore already, but I continue to bend. What does that mean? I bend until bigger than critical angle. It can't go out anymore. It can only go back in. This is critical angle and total internal reflection. So I hope this makes a lot of sense to you now. The conditions for the next page is common, but I shall not, or rather the conditions of this is commonly tested, but I shall not run through it for now. I want to jump straight into the question before we go back to lens for the last part. You can follow along with me to the worksheet first for question 6. Let's discuss this immediately. I want to use the correct answer to discuss with you guys. Answer is option C. We break down the question together first. This ray of light is incident on one side of the rectangular glass block. Angle of refraction in the glass is 40 degrees. I want to find a possible path of this ray, critical angle 42 degrees. The diagram look pretty similar, but what we can recognize is, let's look into the correct option to correctly break this down. Question already tells me that this is 40 degrees. Therefore, what I can say is, if I extend the normal down this way, 90 degrees in the right angle triangle, right? I can see that this is actually 50 degrees. This 50 degrees, people, is your angle of incidence. So your angle of incidence over here is 50 degrees. This is greater than your critical angle, 42 degrees. 42 degrees in the question was given as the critical angle. Therefore, this is the scenario where I push the person beyond her limits, such that she explodes. Therefore, what I'm trying to see here is total internal reflection happens. Therefore, option B is out. Therefore, option A is out. Option C and D are what I'm left with. So the last part will be how it will bend when it goes out. And I think this is a bit more obvious, because when it goes up into air, I go faster. If my FAST go faster, means I bend away from the normal. Option C is the only possible option. All right, I'm moving. Question 7. Again, I'm focusing a lot into TIR. So I want to debunk this for you already. Refractive index 1.4. From this refractive index 1.4, right? Question tells you that the angle of incidence, angle of incidence over here is 70 degrees. Intentionally, they told you that light undergoes total internal reflection, which means that angle of incidence must be greater than critical angle. Make sense, right? Because TIR took place. TIR took place means that 70 degrees is more than critical angle. That's it really. From this question is pretty easy to solve, I guess. Because what you can see from here is actually that the critical angle must be less than 70 degrees. And the refractive index of the plastic immersed in a liquid, like traveling in the plastic tube. So this is the plastic, then this is the liquid. Okay, so light is trying to travel from the plastic out to the liquid. If TIR took place, it must mean that plastic is denser compared to the liquid. Because this is condition number 2 for total internal reflection. Okay, therefore, the refractive index of plastic must be greater than 1.4. Answer is option C. Okay, a final point that I want to cover, right? For refractive index 1.4, how can I calculate the critical angle? Okay, hear me out over here. Typically, schools are just going to tell you, students, the fourth formula to calculate refractive index is 1 over sine C. Okay, and if you are tested for this for WA1, I'm sure you know this. Hear me out. Help me be able to understand why this formula works. Okay, I want you to be able to derive this on your own. Why? From the very first thing that we said for refractive index, right? We went with n equals to sine I over sine R. What is the I and R in this case? Sine I is your 90 degrees when the angle of incidence is too big until my angle of refraction is 90 degrees. And your angle of incidence is literally your critical angle. You punch sine 90 degrees into your calculator, you will realize that sine 90 equals to 1. Therefore, n equals to 1 over sine C came about as a result. Okay. To make this a bit clearer, some of you will be more comfortable with sine R over sine I. That's perfectly okay. Okay, because in this case, we are talking about the critical angle being the angle of incidence. Then the angle of refraction is 90 degrees. Yep. So I'm trying to use this question to actually make you be able to understand the derivation to this. Okay, that's it for the refraction questions that I'll be running through. The last point I have is lens. Okay, and without going into the content first, this question 8 immediately think about it. Help me think about it for at least a good 15 seconds. I'm going to drink 2 sips of water while you're trying to think through this question. Okay, which one is converging? Okay, for those who are thinking option B, option B is not correct. Okay, and let me explain to you why, so that you will understand this forever. Okay, the answer is actually option A. I show you why option A is correct. Option A, if I continue to extend the ray as if it didn't bend, what will happen? It actually bends inwards. Therefore, option A is converging because it bends in. If you chose option B, looks very correct. Okay, but same thing that I want to warn you of is in light, how can you properly determine for refraction, like whether it bends away or towards the normal? I extend such that it didn't bend. Idea is therefore like this. If I extend the ray as if it didn't bend, I see it actually bending upwards. Therefore, this is actually diverging. Okay? So don't take info as what it is. Okay? So because you see this like coming closer together, probably converge. Okay? It's actually not true. Okay? So now to approach this kind of questions. Okay, I'll go with the content before we finish up with the questions for lens. Content for lens, right? I won't go into the terminologies anymore. Just one terminology that I need you to understand is focal plane. Focal plane is misunderstood, misinterpreted, underrated by too many teachers and students already. Focal plane is this imaginary line over here that cuts through the focal point. Are all rays going to pass through the focal points? The answer is no, it won't. Okay? But parallel rays, for example, if I have parallel rays going through this way, are they going to hit the focal point? No, they won't, but they must converge somewhere along the focal plane. Okay, so that's what the focal plane is about. Focal plane is along the focal point. It must pass through focal points. Okay, and it will be perpendicular to the principal axis. Okay, then I want to go into the idea of the ray diagram. Okay, as a quick overview first, to draw ray diagram, I definitely always need the line that passes through optical center. This ray is compulsory. Okay, and this ray over here is actually not going to bend. The idea is because we are entering at angle of incidence 0 degrees. Make this link for yourself here. Refraction is actually linked to lens. The reason why light ray bends when I go into lens is because of refraction. Okay. So this compulsory line must draw first. Next will be straight away into this really. Okay. If you are a big hater of this, right? Let me assist you in visualizing this in a way that will change your life. Okay. For my students in my class, this one I usually use another concept that I want to bring this idea out. Okay, but I'll give you something quite similar. Okay, which is like how to properly think about this entire thing, such that you don't need to study so hard for. Okay, personally as a student, I hated this thing. Okay, if you are similar to me as a student, right, hear me out. Okay, lend me your ears for the next 2 minutes. What I want you to start off with is always this u equals to 2f. U equals to 2f should be your starting point, because this is your same size photocopier. Okay, this you can take it as the first reference point, then you start shifting your object and start shifting your image. Okay, so this is the position where I have the same size of object and image, and the object distance and the image distance is also the same. U equals to V equals to 2F for this first diagram. Following which, when I start to shift the object away, notice that the image shifts accordingly as well. Okay, so if I have this as a starting reference point, when I shift object to the left in this diagram over here, object moves left, image also moves left. Image is now smaller. Okay, with drawing, you definitely can see this, but what I want you to see is like how to study this in a more effective way. Okay, my students uses a slightly more in-depth approach to visualize this. Okay, but I shall not reveal it here. Okay. So what next, right, is after you shift the object to the left, now you try to go back to the reference point, shift the object to the right. If I shift object to the right, my image is also going to shift to the right. That's the idea already. And you see what happens to your image becomes magnified. Okay, so the reference point, you start from 2f. Then you shift object to the left. Object distance become larger than 2 focal length. Image must also shift together. Okay, but when I shift object to the right, image also shifts to the right. Again, shift together. That's it already. Okay, I would say this, and this should be your main focus, because these are the ones that you are usually tasked to draw in exam. Later, the very last question that I will go through will bring up one of the curveballs that I feel a lot of schools don't cover, but some schools love to test. Okay, so hear me out until the end, okay, because that question is really important. Okay, so with this, pretty much we have covered this 1, 2, 3 already. So the last one that I just want to show you is this: when I decrease the image, or rather the object distance until it is less than 1 focal length, this is image being formed as a virtual image. Okay, and this is your magnifying glass. The simplest idea to study for this, right, is if you think about how the old folks like to use magnifying glass to read the newspaper, right? How close do they put the magnifying glass to the newspaper? They must put pretty close up. They cannot like that, right? They put at their eye like that and then try to read the newspaper. Doesn't work. Right? Simply because of this lens idea. So they need to put the lens near to the object, pretty much less than one focal length. Then they will be able to see the image being magnified. Okay? The image being formed on the same side of the lens suggests that it is a virtual image. Okay, so what I want you to take away from this is you start from this reference point to F, then you shift accordingly. That's it. Okay, I'm going to jump to the questions now. The questions that I will go into will be question 9. Okay, those kind of questions, I want you to be able to break down when you see certain things in the question. Okay, number 1. Object 6 cm from the center of the lens. This is pretty much your object distance. Okay, question tells you, oh, virtual image being formed. In your head, should be like, oh, I know that this is confirmed magnifying glass. Example. Therefore, your object distance will be less than 1 focal length. Okay, but what you need to see from this question is when I draw something, when I draw a ray that is parallel to the principal axis, it must bend and hit your focal point. Therefore, this point is your focal point and 10 cm equals to your focal length. That's it. Okay, so when it's placed 20 cm away, 20 cm is literally 2 focal length. Okay, if you studied the first reference point in the very sick diagram that you guys hate, right? Okay, I shall not scroll back. Okay, but if you hate that entire ray diagram, if you know the first reference point as the 2F, everything same one, you're done. U equals to 2F, V equals to 2F. You're done. Option A is your answer. How far is the image from the center of the lens? Is asking you for your image distance. Okay. Okay, and this should make sense to you, right? Because this object distance that's shown in the diagram, right, is 6 cm. 6 cm is less than your focal length of 10 cm. Therefore, virtual image. Okay? But question is meant to distract you with that. They really want you to see this. That the focal point is actually here. So that focal length is 10 cm. Right? To finish things up, I'm going to take a look into the lens question. Okay, 10A, I'm not going to ask you to draw this, nor am I going to show you the scale diagram. Okay, but what I want you to see is, right, this kind of questions, how do you check your answer even before you draw your diagram? Okay, question wants me to focus into data set 1, right, which is this. Okay, data set 1 shows you all of this. What I need you to pick up is the following. Okay, so when you see this in WA1, right, go and try to study properly first before you should be like scramble to draw. Object distance 30. Image distance 30. Object height 5. Image height 5. Everything is the same. What do you think we are doing with this? This is literally your situation, your scenario of U equals to 2F. Right? Because U equals to 2F, V will also be equals to 2F. Image and object both same height. Therefore, this is your scenario. When you draw, to check your answer, focal length must be therefore equals to 30 divided by 2, 15 cm. If you deviate from this 15 cm, you are likely to get it wrong already. Make sense? Okay, so I'm not going to show this drawing here. I want to go into question 11 to show you the drawing. Okay, but this is exactly what I want you to see from this kind of questions. Okay, if you're wondering how to draw, the first step to drawing a ray diagram, right, is always go and draw your principal axis first. Principal axis draw in your lens. Then you work from there. Okay, so just to give you a starting point for this. 10B and 11A is what I will end off with. 10B, the real and upright image to be obtained, can be done by the following. Object AB is like shooting out rays, right? So rays are coming out this way and this way. You know the image is going to be inverted already, but question wants it to be upright. What can you do as a result? Add in another lens. Why? Question is trying to test you for two things. Number one, when I cut through the focal points, they must go parallel to the principal axis. After which, when I put a lens over here, if it is parallel to principal axis, it is going to bend and hit the focal points. Therefore, your answer will look like this. Done. So that your A and B are going to be here, you're going to obtain an upright image. Okay. My final point to sum everything up today will be the following. Okay. To get you to stay to the end with me, okay, after this, I'm going to splash the QR code for you to leave a Google review. Then the top Google review always win prizes. Yeah, okay, so you're baited already. So stay with me here. Lens is converging or diverging, same thing as what I have discussed already. You extend, you see it bending inwards towards the principal axis, definitely converging. Okay. What I want you to see from this question is actually how to draw ray diagram if the object looks damn weird. Okay. We are very used to object must usually look like that. Do they need to? They don't. Look at this object over here, damn weird. Like cut through the entire principal axis. Do you need to panic? No need to panic. Okay. What you should do in exam is relax first, then you think about what is the compulsory way to draw. Okay, compulsory way to draw. Oh, I remember. Because I attended today, right? Just say I must draw through the optical center. Okay, this is exactly what you need to do. You draw a ray through the optical center. Can make sense of this, right? Okay. Now that this is drawn, right? What I need you to do next is the following. What will happen to this ray as well? You can see that this ray is like going away already. Okay, are they ever going to meet? They are actually not going to meet each other. Where do you think we are going with this? We are actually going to form a virtual image. Okay, and where will the virtual image form? When I dot this backwards, this is where they are going to meet. As a result, you are able to determine the focal points by the following. Okay. Let me intentionally draw this in the last color that I will use. I'm going to put in this pink color. Definitely there will be a ray that goes like this, but my point is I don't know whether it's going to be here, here, or here. I'm not so sure. Okay, so what I need to do is I place my ruler down. Whatever it is, when I trace backwards, it must also pass through this point. Therefore, this ray must continue on straight this way. My principal focal point will be therefore at this exact position, F. Can make sense of this already? Okay, so this is what I mean by this question is a bit strange. The object is a bit strange. Okay, but I don't think I have fully answered some of your queries yet. Okay, so let me leave the best to the last. Okay, because you all will be like, this object really damn weird. How come the thing is like cut through the principal axis? Then what about the point below? What we can see is that definitely my image is going to be here. But where does it end? This is where I can draw one last ray to finish this off. Whatever, or rather wherever the ray starts from the object, it must end at the same place for the image. Okay, so if I draw one ray from the bottom here, same thing. I can draw a ray that cuts through the optical center because that is always your compulsory ray. since they are never going to meet, right? What happens is when I dot this backwards, this is where I can see where my image is going to end. Therefore, my image is actually here. Okay. And my point is the following. You are going to see weird questions for sure. The weird questions that you will see are things like, maybe the object is like above. Maybe the object can even look like this. This question, object literally cuts through the entire thing. What do you do in exam? Don't panic. Go with the idea of, I draw some light rays from the top of the object. Then I draw some light rays from the bottom of the object. Whatever it is, it must end at the same position of the image. Okay, that's it. If this is exactly the answer for this question 11, I would say question 11, if you understood what I was going through, you are going to upgrade in length for sure. Pause for dramatic effect. Okay, you may have some question lingering in your head, okay, but I'm actually done. Okay, this is it for my brief 1.5 hours overview of waves and light. Okay, I hope this debunked the myths, the questions that you still had inside your head. Okay, I'm going to be flashing the QR code to scan to drop us a review. Yeah. Okay, so the top review will receive a set of creator notes worth $40. Okay, I don't know whether you got see the Google reviews before, but then those like usually like very sincere ones are usually the ones who will read. Okay, so make it lengthy. Quote my name, quote my name. Let me put down my name. Okay. Hope I managed to help you. So this is me. This is my name. Okay, I put it as big as I can. Anyway, I'm here. This is me, guys. Okay, anyway, if you enjoyed this session or even if you didn't, okay, I hope you can leave a Google review for us to say whether you have enjoyed this or whether I helped you or not. Okay, that's it. The answer key I think I have given to everyone already after going through this entire video. Okay. Once again, I thank you for your time. Okay, I know students' time are very precious. I hope your dinner plate is like done, not like still left with like one whole bowl of rice or something like that. Yeah. Yep. But that's it. I'm gonna leave this QR code for a while. The last part I will be showing you will be in the event that you are interested in some of the schedules. I'm just going to flash the schedule at the end. Okay, but if you have scanned this and you are good already, and you have nothing left to say to me, uh, you are good to go. Okay, so I really hope you enjoyed this session, and I thank you for your time. If you need the QR code, you let me know again, okay? Okay, I'm moving. Yeah, so we are Sec 4, so I will go straight to the Sec 4 classes. Pure physics. Yeah, it's here. So basically for me, I teach at both Kovan and Woodlands. So if anything, I will definitely be there. Okay, I zoom in a bit because a bit small. Here. Okay, so personally, my sessions are where Gerald is lah. Okay. If you're interested, you can take a look. If not, if you need a QR code, let me know. If not, that's it. Thank you and bye bye. I'm gonna stop the recording first.